All right, let's go ahead and get started. So the plan for today, the plan for the review session today, I'm planning to give it in two parts. And the first part, we're going to talk about structures and the various mathematical structures that we've encountered in this class. And that includes logic, sets, functions, relations, and I plan to spend a good amount of time talking about finite automata. On the second half, we're going to focus on combinatorics and probability. Each of those sections, I'm planning for them to take approximately like 75 minutes. So, I mean, assuming everything goes according to plan, we'll still be done by the scheduled 7 p.m. But I anticipate we might have to go over. As long as this room is not reserved over, I'll try to at least cover everything that I plan to cover. And of course, now that the recording is working and the Zoom is working, everything will be recorded and uploaded so that if there's any part that you missed or want to watch again, I'll post the recording so that you guys can watch them. So let's go ahead and get started with the simplest structure that we've seen in this course, and that is the notion of truth and falsehood. And in order to talk about whether something is true or something is false, we use the language of propositional logic. Propositional and predicate logic. And its goal is to model, oh boy, the video is backwards. There we go. All right, so in order to model propositional and predicate logic, so the goal of propositional and predicate logic is to model truth and falsehood. And in math, we're always concerned with what's true and what's false. In order to justify that things are true, we use proofs, and in order to show that things are false, we use counterexamples. And in order to have a language to speak about propositions, we're going to have variables, let's say P, Q, although these letters themselves are not important. They could be A, B, C, D, or whatever. And we're going to have these variables here, and these variables are going to represent propositions. And what are propositions? Propositions are statements which are either true or false. Therefore, when we have a variable which is representing a proposition such as P or Q, the value of the variable P can only be a Boolean value. It can only take on a value of true or false. There is no meaning to say something like P equals 5, because P itself is representing a proposition, not a number. And propositions don't take on numerical values. They take on Boolean values of true and false. Now, in algebra, when we have variables like x and y, we have operations by which to connect them and to create more complex expressions. For example, we can have something like, if we have variables x and y, we can do x plus y, x times y, x minus y, etc. Analogously, we can also have operations on propositions. And these operations necessarily are different from plus, times, minus, and things like that, because we are operating now on variables which are true and false, and not variables which take on numerical values. And so these operations are defined via the truth tables. And you can think of this as if we were to define what addition, multiplication, subtraction, and things like that are by enumerating all possible values of x and y and then writing out what the result would be. For example, if we were to talk about what x plus y means, I can say, well, if x is 1, y is 1, then x plus y is 2. And by listing out all the possible values, then we can define what plus means. It's usually not the way we do it, because you would have to therefore list out an infinite number of values. In the case of adding two real numbers, you would have to list out an uncountable number of values. And so normally that's not the way we define things in terms of algebraic variables. But in terms of propositional variables, P and Q, we can define operations on them by enumerating all possible values that P and Q can take on, because P and Q can only be true or false. So therefore, we have a finite number of possible combinations of what P and Q can be. And so I'm going to write out here the truth tables: true, 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 false, false, true, and false, false. So we have P and Q, P or Q, P implies Q. I probably forgot one, not P, and also P if and only if Q. And not P, and hopefully these operations are intuitive to you, just as when we talk about plus, you talk about like adding something. Here we're talking about and, or, implies, and if and only if. This is not, and, or, implies, if and only if. And the truth tables are given as follows.
I love Justin.
I'm not going to speak too much about how these about these truth tables. Hopefully their definitions are intuitive to you, that if I want P and Q to be true, I require both of them to be true. And if even one of them is false, then P and Q is false. And similarly, I hope the intuition is clear for the other ones. In particular, I'd like to address P implies Q, because in most of the statements you're asked to prove are somehow of the form P implies Q. Because normally you have some kind of precondition, some kind of assumptions that you have, and via those assumptions, you derive a conclusion. The assumptions, the conclusion. And in order to prove a statement P implies Q, so in order to prove something P implies Q, you would assume P, and then you do something, and then to conclude with Q. And so why is it the case that you would assume P? Why is it the case that we wouldn't even have to consider the case where P is false? Is because when P is false, we don't even care what Q has to be. Q can be anything you want. If P is false, P implies Q is automatically true. So therefore, there is no need to even if P is false, nothing is under consideration, because if P is false, we're immediately have reached the fact that P implies Q is true. Only in the case where P is true is there some doubt involved as to whether or not Q is true. And so in order to prove P implies Q, I assume P, I put myself inside this scenario here where P is true, and I need to justify that whenever P is true, I'll never end up in this case. I'll always end up here. Therefore, that P implies Q is true. In order to prove an if and only if statement, we prove P implies Q, and we prove Q implies P. And I'm not going to justify this here, but if you were to work out the truth table for P implies Q and Q implies P, you will realize that that is equivalent to P if and only if Q. I now want to talk more about, I hope these ideas of propositional logic are clear so far. Thumbs up, middle, thumbs down. All right. Now I want to go into the notion of predicate logic, which is by adding in these ideas of for all x, P of x, and there exists x, P of x. And this for all and there exists represents is that whenever we say something like for all x, implicitly there's a set that we're talking about behind it, like all of what. So if I say something like for all students, you have a student ID. So if P of x, so x here is a student, is that you have a student ID. Implicitly, when I say for all x, P of x, when I say for every student has a student ID, and so implicitly there's always a set hiding behind these statements, which tells you what you are quantifying over. So like if I say for all x, p of x, where p of x, x has a student ID, the context dictates that when I say for all x, the set over which I'm doing the for all is like all students. I want to, in order to illustrate the behavior of these for all and there exists, I'm going to do an example which should come from question 4 on the review sheet. And this talks about the notion of what it means for a sequence to converge. So intuitively, in some calculus classes, you may be already familiar with what it means for a sequence to converge. If I write down a sequence something like this, 1, 1/2, 1/4, 1/8, 1/16, and so on, intuitively, you already feel that this sequence is converging to 0. It's getting close to 0. I could give a different example. Maybe if I did 1/2, 2/3, 3/4, 4/5, and intuitively you could feel that this is getting close to 1. It's converging to 1. Now, the formal definition of convergence requires the behavior of these quantifiers for all and there exists. And so if I have a sequence, say S0, S1, S2, and so on, this definition itself is not on the exam, but I'm using this definition as an example on how to deal with, I've erased the quantifiers, but how to deal with quantifiers. So what it means for S0, S1, S2 to converge to L, I'm going to write out this first, and 0 and implies and so this definition at first is probably kind of confusing. I'm going to draw a picture for it, which will hopefully clarify things. Let's say that here I've graphed on the x-axis the values of n. So here's 0, then 1, 2, 3, 4, and so on. And on the y-axis, I graph the values of the sequence. And so let's say here I have my L. It converges to L. And let's say that my sequence goes something like this. I'm not going to label too many values, but let's say it does something like this. And it's getting closer and closer. Let's take a look at how this statement works. For all epsilon greater than 0, for any epsilon greater than 0, what is this epsilon doing? So whatever epsilon you have, give me, there exists some n. And what property does it satisfy? As long as I'm past this threshold n, all my values of the sequence are within epsilon of L. So the first thing you want to do when you're confronted with perhaps a complicated predicate statement like this is to determine what the roles of these variables are even doing. And so by looking at this, we can see that epsilon itself represents a buffer room. Epsilon represents a buffer room that I can deviate from L. So here's epsilon, here's epsilon. N here is a wall. As long as if I know my little n lies right here, greater than big N, this implies that all my values that implies that my value s of n lies within the buffer room, within epsilon of the L. So what this is saying is for all buffer room, I set my buffer room epsilon. For all buffer rooms that I get set, there's always a wall by which when I pass over greater than this wall, all the values of the sequence are within the buffer room of the limit. This definition itself, I hope, we're not going to, the idea is that this definition proper is not on the exam, but we're talking about how to think about these quantifiers. I want you to pay attention to one thing here, which is that this n need not be the same for all epsilon. This n, what this statement is saying, for every epsilon, for any epsilon that I pick, there exists some n which works for that epsilon. This n is specific to what epsilon I pick. What this is saying is that every epsilon has what property? Every epsilon has the property that there exists a wall where past that wall, all my values of the sequence are within epsilon. I'd like to draw a contrast with this to the statement, there exists n greater than 0 such that for all epsilon greater than 0, n I'd like to draw a contrast to the second one. The second one is saying there exists this wall. I can find a specific wall for which every epsilon that I pick, no matter what epsilon buffer room I pick, I could pick that buffer room as small as I want, as large as I want. There exists this wall such that no matter what buffer room I pick, as long as I'm past this wall, everything's within the buffer room. And so I hope that you can see that from this sequence satisfies the first, but fails the second. This sequence here that I've drawn that's slowly getting closer and closer to L satisfies the first because for any buffer room epsilon that I pick, if I make my epsilon smaller, if I make it like something like this, I just need to go farther out, I'll find another wall. That's the new n. Or if I make the epsilon even smaller, I make it even smaller all the way over here. Like I make it like really, really, really tiny. And then I can go farther out, pick that wall, everything's within the buffer room. By contrast, the second statement is saying there exists this n, there exists this wall such that every buffer room, no matter how small I make it, all my values of the sequence are within there. And then I'll leave this to you to work out on your own. But if you want to satisfy this, you'll need everything to lie strictly on L. If anything even comes off of L, or you need everything to eventually lie strictly on L, exactly on L. Because here, what this is saying is there exists this wall such that past this wall, every buffer room constrains all the values of the sequence. Can I have thumbs up, middle, thumbs down as to how we're doing on this? All right. Want to move on to talk briefly about set theory. I'm going to erase. Everything is recorded, so I mean you're welcome to take photos, but I'm going to try to fit in everything that I can. So I want to after I erase the board, going to talk briefly about set theory and about functions. All right, so as we're moving on from propositional logic, so propositional logic and predicate logic model ideas about truth and falsehood. Set theory talks about whether things are included or not included. And I hope things such as maybe if I write something like this, this is a fairly innocent set. This is the set, these are the elements. But one thing that I want to caution you about, it's just where a confusion could possibly arise, is by distinguishing clearly what is the set and what are the elements within that set. This particularly can become confusing if I make one of the elements themselves a set, notice that in this set here that I have written on the board, there are 4 elements. One is this, one is this, one is this, and one is this. There are a few things about, just as in propositional logic, how we talked about and or, and not, and implies, things, operations that we can use to work with propositions. We also have operations for which we can work with sets. Namely, we have things like A union B, A intersect B, and I'm not going to talk about these too much. I hope these are fairly clear, but I do want to talk about something, A subset B. And the way that the definition of subset itself may seem innocent at first, which is that A is a subset of B if everything in A is in B. I want to give an example here. If I call this set B, this is a subset of B. This is not a subset of B. And how do we check whether something is a subset? Sorry. How do we check whether a set is a subset of another set? Is we go through each of the elements of the subset. So we want to go through each of the elements of the subset and check whether they're inside this other set. So we want to check. We want to go through each element of subset. So in this case, and check if they are in the larger set. And when we're doing this check, it's necessary to be careful as to what are the elements of a set and what constitutes the set itself. In this case, this set on the left has one element. I check, is this element inside B? It is. And since all the since all the elements inside this set are also elements inside this set, this is a subset. But here in this case, I look at the individual elements. I look at the individual element C, and I ask whether C itself is in B. C is not. Therefore, this is not a subset of B. A few other points about operations involving sets. I want to also talk about the power set. So the power set, here I'm going to talk about power set of B, is the set of, so the power set itself is a set. Its elements are the subsets of B. The power set is a set. The elements of that power set are the subsets of B. And so what's inside this power set? The empty set, the set containing the first thing, the set containing the second thing, the set containing the third, the set containing the fourth. I can also do the set containing maybe the first and the second, the first and the third, and so on. And finally, I want to address one final thing about sets, and this is the Cartesian product. A cross B is a set. The elements of this set are ordered pairs. Let's call this A, B. The ordered pairs, the first element in the ordered pair comes from this first set A. The second element in the ordered pair comes from the second set B. And so if I were to give an example, maybe if I can make some small sets here, A is the set 1, 2, B is the set 3, 4. The Cartesian product A cross B is the set of pairs. The elements of the set are pairs, are ordered pairs. The first thing, it's the sets of all ordered pairs where the first thing comes from the first set, the second thing comes from the second set. So here I have the 1, 3. I can also do 1, 4. And likewise, I have 2, 3, and 2, 4 as well. Here. Are we all good? Thumbs up, thumbs down about the set, about things regarding sets. I'd like to now move on to the idea of functions. And as we're progressing through functions themselves, model an input and an output relationship. We're talking about if I input something, what do I get out? And so the way I want you to think about functions in this class is that we have a set here. I call this set the domain. I have a set here, the codomain. I have elements inside here. I'll call this maybe X, Y. And we're going to do these kinds of mappings. When we have a function, the word function places very strict requirements on what's going on in here. It places basically no restrictions on what is going on in here. The codomain only tells you the set of potential outputs you can get. And I use the word potential carefully because not all the outputs may be attainable. And some outputs may be attained by more than one input. But the word function really doesn't care what's going on in here. The word function is only talking about the domain. And it places very strict requirements on how these arrows are going to work in the domain. In a function, every element in X must have exactly one arrow pointing out. In other words, I can't leave anything to have no arrows, nor can I have one input generate two outputs. When we want to place restrictions on the codomain, on what the arrows are doing inside the right-hand side, that's where we talk about injective, surjective, and bijective. And so a function has already placed very strict requirements on what happens inside X. Every single element in X has to have exactly one arrow pointing out. And the words injective, surjective, bijective place requirements on the right-hand side on how the arrows come into Y. And I want to give an informal definition. Injective is that so elements in Y, if they have at most one arrow, that's injective. At least one arrow, surjective. Exactly one arrow is bijective. I'd like to also talk about these things in terms of the left and right inverse. So let's say I'm So I'm going to so that I have a little more space.
I think it's really obscure. So I'm just gonna look at like the scale of evolutions. Same thing with coefficients. Like I think it's also really obscure. It's like really.
Suppose I have a function which is,
So
I'm going to draw maybe a function here. Say x, here's y, y. I'm going to draw one that's injective. A left inverse is a function that goes from y to x, goes the other way, such that f inverse of f of x equals to x. I hope to give you an intuitive explanation for why an injective function must contain a left inverse. So injective must have left inverse. What this left inverse is doing, and so the way to remember that this is the left inverse is that the inverse is going to the left of this function. And how I can see that an injective function must have a left inverse, let's look at this formula here. I'm going to take x here, and I'm going to plug it into f. I'm going to take some x here, and I'll plug it into f. And what this left inverse function are the arrows going this way. They're going from y to x. What this left inverse function has to do is I plug in an x, I take it through f, and my left inverse has to take it back. So here I get the left inverse. Now what happens with these? Well, these I can assign them to whatever I want. I can do this, I can do this. It's not too important because all I need to worry about is whenever I plug in an x, I plug it through my function f, the left inverse takes it back here. And why is injective important for having a left inverse? Because if it weren't injective, let's say we had a second one here that's also coming up to here, then we can no longer get this left inverse. Because if I made my left inverse point back here, I take this, I plug it in, I come back here. But I take this, I plug it in, my left inverse is going to take it over here. It's not going to give me back x. So an injective function is going to have a left inverse. We can do a similar thing for a right inverse. Which is a function going from y to x, where f of f inverse of y equals to y. And surjections must have a right inverse. Again, I'm hoping the bubble diagram here, I'm going to draw this bubble diagram, will help give you an intuitive idea as to why this is true. Let's say we have something like this, this. What the right inverse says is, I need this function y so that I first start from y. Remember, the right inverse goes from y to x. It starts here and comes here. I plug in my y into my right inverse, and my original function needs to return it home. So let's say I plug in this one. I can pick maybe this one to be the output of the right inverse. From here, I can maybe pick this one to be the output of my right inverse. And I can check this. If I plug in a value y, I follow the right inverse here, and I follow the original function back, and I'll always end up in the same place. Notice that this is not possible if this is not a surjection. Suppose I had this extra one down here that's not mapped to Now, if I wanted to generate some right inverse, well, I'll have to assign this to somebody. Maybe I'll assign it here. Whoever I assign it to, let's say I take this y, I plug it through the right inverse, I follow the dotted line over to x, whatever I plug in, well, nothing's going to return it here because f can't even return anything here. This thing is being left alone. Therefore, a surjection must have a right inverse. A bijection, since a bijection is injective and surjective, it has both a left and a right inverse. Very good. Thumbs up. All right. I want to briefly also talk about the way we compare the cardinality of sets using functions. I'm going to pull this up.
Sections are all maps. Oh, why are all maps? Just like, yeah. That would make life.
All right, so if we want to compare the cardinality of sets, we want to compare the sizes of two sets. If the sets themselves are finite, we essentially don't have much to do because we can just say this set has 5 elements, this has 7 elements, 5 is less than 7, this set is bigger than the other, this set is smaller than the other. This gets sticky when we need to talk about infinite sets. And especially the whole idea about talking about cardinality really gets interesting when we are talking about infinite sets. And in order to talk about infinite sets, it doesn't really it's difficult then already to say, well, this infinity is less than that infinity, or we have like, this infinity, that infinity, is infinity less than infinity, is infinity plus 2 less than infinity. And so the way to define the comparison between the cardinality of sets is via the idea of functions. And so we can say, we would write something like this. We would write something like this when there's an injection, when there exists an injection A to B. We'll write this when there exists a surjection A to B. And we'll write this when there exists a bijection A to B. In particular, what is of perhaps greater interest is not just these, but comparing the sizes of sets to the natural numbers. And we want to talk about whether, because we know that so when we're talking about infinite sets, we know that the natural numbers are infinite in size, and we want to compare, like, is this set bigger than the naturals, smaller than the naturals, equal to the naturals? And so what it means to be countable is that there exists an injection from the set A to the naturals. We can talk about countably infinite this is that there exists a bijection from the set A naturals. And so the way to show that a set is countable or countably infinite is to demonstrate such a function, and then is to demonstrate such a function and prove that that function that you have given is in fact either an injection or a bijection. For example, I can show you that the even numbers are the same cardinality as the naturals. And how I would do that, how I would show you that perhaps the even numbers are equal in cardinality to the naturals, is that I can if I put down the even numbers, the even naturals 0, 2, 4, 6, 8, and so on, and I put the naturals here 0, 1, 2, 3, 4, I can demonstrate a bijection from the evens to the naturals by perhaps like dividing by 2, like divide by 2. Now, we also have some sets which are greater in size than that of the naturals. And that's what we call something that's uncountable. Uncountable, which is that there is no injection. There's no injection from A, the naturals. I believe you have encountered some such sets in this class, including something like the power set of the naturals, the real numbers, and the way that was proven was by diagonalization. I don't want to go into too many of the details of diagonalization, but I want to give you perhaps another technique which might be useful in showing that a set is uncountable. And one of those, I'd like to say there are 2 ways to show that a set is uncountable. The first is via diagonalization, which is the way you might prove that the reals are uncountable or the power set of naturals is uncountable. But another way you can show that something is uncountable is you can show that that set has the same size as another uncountable set. If you show that some set, like set A, has the same size as another uncountable set, then you know that that set is uncountable. And I want to give a small example of this. Suppose we wanted to show that, let's say I have a finite line segment here. Let's just say it's of length, I'll make it an open line segment. So we're not including the endpoints. Here's 0, here's 1. Let's say we want to say that the points on this line segment are uncountable. Perhaps perhaps we've already shown this via there is a way to do this via diagonalization. But let's say we know that perhaps the reals are uncountable. Let's say we know the real numbers are uncountable. How would we show that the number of points along this line segment is uncountable? Is by demonstrating a bijection between this and the reals. So you can think about the real line as something that's extending infinitely in both directions, this real line here. And I want to show that there's a bijection from this to this. Now, one thing you might think about doing is, well, a bijection, we have injection, surjection. Maybe I want to show an injection from here to here and a surjection from here to here. That is one possible strategy, and it's one that is actually a good strategy. In fact, I want to mention to you a theorem, the Schroeder-Bernstein theorem, which is that if you have F, A to B, injection, and G, which is going from B to A, surjection, then there exists a bijection, A to B. What this is saying is that even if I were to find some injection from here to here, and A to B, and some surjection from here to here, if I were to find an injection from here to here and a whole different surjection from here to here, then this bijection exists. In other words, one way you possibly could show that these two things have the same size is that you supply an injection going from here to here, you supply a surjection going from here to here, and by the Schroeder-Bernstein theorem, you know that this bijection, even though you haven't necessarily found it explicitly, this bijection must exist because you have found an injection and a surjection. Here, however, this technique may not This technique is something that is worth trying, but this technique may not work here because how are we going to find the surjection? The injection is easy. I could put this line right on top here, 0, 1, and I can get an injection, right? Everything has at most one arrow. These have none. But to get a surjection is more challenging. You might think maybe we can scale this up, but even if we were to scale this up, even if I were to scale it up, I would never be able to hit the infinite length of this real line down here. And so the one attempt is to supply the injection and surjection. The other, another way that you could do this is to just supply the bijection. And the way I'm going to do this is I'm going to take this line and I'm going to bend it into a semicircle. The semicircle has length 1. It's part of a circle of circumference 2. Therefore, the diameter is 2/pi, so that we have a radius here, 1/pi. Imagine you have a light right here. And this light shines down, hits this point, and hits here. Or this light hits here and hits here. And by doing this, you can demonstrate that there is, in fact, a bijection going from this 0, 1, which I've just bent into an arc, with the real line. So I hope this gives you like a reasonable summary of different ways that you could, in fact, show that two sets have the same size. You can in fact see that that this mapping is in fact a bijection. Is it the case that every single point here is mapped to by exactly one point? It is, because if I want this point, what's it mapped to on the arc? I just connect this with this. It's that one. Is this point here, every point on the real line is being mapped to by exactly one point on this arc. It's right there. And so that gives you, it's a surjection. Is it an injection? Can you get more than one point? Well, no, you're not going to get this point coming down here because this point is coming here. Right. Are there any questions about this before? Yeah. Mm-hmm. No, they can be completely different. Just the first one has to be an injection. The second one is a surjection. And the theorem says that if you have that one injection and that one surjection, this bijection exists, even though you may not have stated explicitly. Yeah. Mm-hmm. I mean, this is not formal proof, but I think it's pretty close to being one. And the other kind of like thing that's hidden behind there is that you have a bijection from this line to this arc, and that bijection is the bending kind of motion. It's like if I want to know what's like a quarter here, it's just a quarter of the way down the arc. Yeah. Right.
Right, whatever. And then this point get it 0 away.
All right, so following our discussion of functions, I want to spend also a little bit of time going over the idea of relations. So functions themselves model an input-output relationship. You stick something in, you get something out. A relation generalizes the idea of what it means to be equal, less than or equal to, greater than or equal to. If you think about these ideas, equals, less than or equal to, greater than or equal to, they in fact tell you that like two things are somehow related. 3 and 5 are related because 3 is less than or equal to 5. And this idea of a relation generalizes that idea. Its formal definition, let's say that I have a set A, relation on A is in fact a set of ordered pairs where x, y, where x is in A, y is in A. I want to distinguish this from the Cartesian product. The Cartesian product is the set of every single possible pair. A relation is a set of select pairs. And for example, I can give you a relation like less than or equal to on the naturals. How might I specify this relation? I can specify it as an ordered pair, and I can specify it as a set of ordered pairs, and what the set of ordered pairs does is it tells you every single pair of natural numbers where the first is less than the second. So I have something maybe like 1, 2 is in the set, 1, 3 is in the set, 0, 5 is in the set, 0, 7, and so on. I specify every single pair for which the first is less than the second. It's important to note that these are ordered pairs in a sense that when I say when x is related to y, it is different from saying that y is related to x. It matters which comes first and which comes second. You can think of relations also as saying like someone is the child of someone else. X is the child of y. That's very different from saying y is the child of x. Now, a relation essentially gives no restriction.
I'm sorry.
The relation itself doesn't really give restrictions on what ordered pairs are inside, what ordered pairs are not. So long as that the set containing the ordered pairs, that every ordered pair satisfies the thing where the first thing comes from this set, second thing comes from this set. More generally, I can also have a relation on two different sets. If I were to have a relation, if I did a relation on A and B, that would be some set of ordered pairs x, y, x is inside A, y is inside B, and I want you to notice that to contrast this with the Cartesian product. The Cartesian product is that every single pair, the first is in A, second is in B. The Cartesian product is that set. A relation is a subset of the Cartesian product. It tells you which pairs are like permissible inside the relation. For example, the less than or equal to on the naturals, the set dictates that only the pairs that are permissible are ones where the first natural is less than or equal to the second natural. Now, there are some definitions. Regarding properties of these relations. Notice that in functions, we have dictated that we gave very strict requirements on what happens in the domain, but had additional terms to qualify what happens in the codomain. Similarly, in a relation, we're giving very strict requirements on what these two elements have to be. But we're not really giving any requirements on whether there's anything even inside the set, or whether just one pair is inside the set, or many pairs, or like what these pairs have to be doing. And so for that, there are properties, the properties of reflexive, symmetric, and transitive. I'm going to give the definitions of reflexive, symmetry, and transitive, but I also want to give maybe an example which will make these things clearer. Let's say we have a relation R on a set. So relation R on this set 1, 2, 3, up to, let's give it 10. And what it means what's inside this relation are pairs AB where B over A is prime. I'm going to use this as a running example for the definitions reflexive, symmetric, and transitive. Reflexive is that this pair, AA is inside R for all inside, let's say S. So R is a relation on S. What this is saying is that R consists of pairs. The two elements of the pairs are both from S. What it means for something to be reflexive is that the pairs consisting of two of the same thing, all of those pairs are inside S. In the case of this relation, is this relation reflexive? Let's do like 2, 2. 2, 2 is not inside the relation because 2 over 2 equals 1 is not prime. In other words, I need this relation to satisfy that whenever I have a pair of two of the same thing, that pair is always inside the relation. That's reflexive. Symmetric. Ooh. If AB is inside R, then BA is inside R. Maybe it will help if I give maybe some examples of things that are inside this relation. 2, 1 is inside. 1, 2 is inside this relation. 1, 3 is inside this relation. 2, 6 is inside this relation, and so on. These are all pairs for which the second thing divided by the first thing is prime. Is this relation symmetric? It's not, because let's say I know 1, 3 is inside R because 3 divided by 1 is prime. But 3, 1 is not inside R. 1/3 is not prime. Right? 1/3 is not prime. Transitive. If the pair AB is inside R and BC is inside R, then AC is inside R. I'm going to use this example again. Is this relation transitive? It's not transitive because what if I had 1, 2? That's inside the relation because 2 divides 1 is 2. That's prime. 2, 4 is inside the relation. 4 divided by 2, that's 2. That's still prime. But 1, 4 is not inside the relation. 4 divided by 1 is 4, not prime. This also gives you a little bit of an example of how to prove and disprove if statements of the form if, like if then. We talked about at the beginning how many of the definitions you're presented with involve if then statements. If something is true, then something is true. And so here what we're saying is if we have a precondition AB is inside the relation, then when I swap them, the pair BA is inside the relation. To prove that an if statement is false, you want to find something where the conditions are satisfied, but the conclusion is false. To prove an if statement false, you want something where the preconditions are satisfied, the conclusions are false. Remember, if you recall back to the truth table of an if statement, the only time the if statement is false is when the part after the if is true, the part after then is false. Therefore, when I provided such a counterexample, I provided a counterexample 1, 3, where 1, 3 is inside R, the preconditions are true, the conclusion, the swap 3, 1 is false. We also have one more property, anti-symmetric, which is that if AB is inside R and BA is inside R, then A is equal to B. In this case, this is a little bit trickier for this relation as to whether or not it's anti-symmetric. Because when do I ever have it that AB is inside R and BA is inside R? If 1, 2 is inside R, 2, 1 is not inside R. So essentially for this relation is in fact anti-symmetric because I never actually get these two things to ever be satisfied. This relation is anti-symmetric because the thing after the if is always false. And if you remember back to the truth table, whenever the thing after the if is always false, it doesn't matter what's happening after. That if statement is always going to be true. This one is anti-symmetric. I'm going to use these properties now to talk about partial orders and equivalence relations. And partial orders and equivalence relations effectively generalize what it means for things like less than or equals to or equality. They effectively generalize on the properties of those relations. So what is an equivalence relation? Well, an equivalence relation is one that is reflexive, symmetric, transitive. I hope it's also clear that these properties work for your standard equals. A is equal to A. If A is equal to B, then B is equal to A. If A is equal to B and B is equal to C, then A is equal to C. I hope it's clear that you can verify that your standard equals works. But I don't need to define something for something that's standard equals. What this equivalence relation lets me do is it lets me generalize what it means to be equals. In other words, I continue to hold the structure of equality without being restricted to the exact fact of like A equals B, B equals C, or something like that. For example, if I want to define, I could say, well, two things are equal if they're the same parity. In other words, if both of them are even, they're equal. Both of them are odd, they're equal. And so in a sense, if I define equals, let me write this equals as same parity. This relation, remember, a relation is effectively still a set of pairs. What's inside this? It's all the pairs where this and this have the same parity. And so, for example, I could have something maybe like 1, 1, 1, 3, 2, 2, etc. And I hope that you can verify for yourself that this relation is in fact reflexive, symmetric, and transitive. Now, what's the idea of the equivalence class? Is that an equivalence class, if I want, so the equivalence class tells me what other elements are equal to something. And so when I say the equivalence class of an element, let's say A, the equivalence class of A is a set containing of all the elements B where A is equal to B. I'm using equals in quotes because this is an equals that I've defined here as meaning to have the same parity. For example, here, if I define equals to be having the same parity, what is the equivalence class? What's the equivalence class of, let's say, 1? Well, that's all the odd numbers, 1, 3, 5, 7, because all of these things are equal to 1 under this definition of equals. What's the equivalence class of 2? It's 2, 4, 6, 8. Because these are all the elements which are equal to 2 under the definition of equals that I have here. A special property of equivalence classes is that the equivalence classes partition the set that you're dealing with. Here we're comparing natural numbers. So here we're talking about the set, we're talking about natural numbers. And notice that the two equivalence classes, this and this, partition the natural numbers. In other words, every natural number is part of exactly one equivalence class. Every natural number is part of exactly one equivalence class. I can take a natural number 10. Which equivalence class is in? It's in this one. I take a natural number 15. Which equivalence class is it in? It's in this one. If in effect, the equivalence classes take your whole set of naturals and chop it up so that everything gets covered and nothing gets covered more than once. A partial order, I'm going to change this board. A partial order, I'll keep that up, but a partial order is one which is reflexive, antisymmetric, and transitive. Partial order is one which is reflexive, antisymmetric, transitive. And the notion of I'm not going to spend too much time talking about this, but I hope that you can see that a partial order in effect generalizes the key properties of things like less than or equals to. Less than or equals to is reflexive because if I have two of the same thing, 2 and 2, 2 is less than or equal to 2, 5 is less than or equal to 5. It's antisymmetric because if 2 is less than or equal to 3, let's say 2 is less than or equal to 3, and 3 is less, well, I mean, that's not true. But if A is less than or equal to B and B is less than or equal to A, then A is equal to B. And it's also transitive. For example, I could say 2 is less than or equal to 3, 3 is less than or equal to 5, therefore 2 is less than or equal to 5. And if you if you talk about this in a different way, if you can, just as we talked about equivalence relations, we can redefine what it means to quote unquote be less than or equal to, as long as your relation satisfies these three properties. I want to spend the rest of this section talking to you about DFAs and finite automata. I'm going to erase the board, and that's what we're going to do right after.
What is that? That's
Yeah.
But
Yeah. Yes. Yes. Yeah. It's whatever set you're going over. So if your set is not necessarily the naturals, it could be real numbers or whatever. Whenever you take all your equivalence classes, they will always partition the set that you're talking about. Yes. Yes. Well, if you're doing your relation on a different set, then it will all be adding up to that set. Not necessarily. Right. Right. All right. All right. The final topic that I want to talk about in this section is that of finite automata. And the motivation for a finite automaton is the idea of string checking. We want to talk about what strings are permissible and what strings are not. I want you to think about this analogy in your head for a finite automata is, imagine if you're writing a form and you have to fill out an email field. You want perhaps the computer to check that the email is in the right form. Perhaps you want some letters and then an @ something.com or something like that. And so in effect, the whole idea of finite automata is that of string checking. You can even think about this, in a maybe a very fancy way, is that someone can check whether you've written a program with at least some measure of correct syntax, you know, like if you misspelled the word if for a while or things like that. But in effect, the idea of a finite automaton is we want to talk about what strings are allowed, what strings are not allowed. And there are three ways that we have perhaps talked about that are three formulations of this idea of string checking, this idea of checking whether strings are permissible or not, all three of which are equivalent due to Kleene theorem. And the three ways that we've talked about are languages, regular expressions, DFAs. Languages are sets of permissible strings. The regular expressions, maybe we have something like A star B, B plus C. What this is saying is I need zero or more A's followed by a B and then followed by either a B or a C. So they give you maybe like a more concrete way to visualize what the string looks like. And in DFA, we do something maybe like this. And what this DFA is, it's a pictorial representation of what strings are permissible. And how does it pictorially represent that? Is you can imagine when you have a DFA that what strings are permissible, what's not. Think about the string as an instruction for how you are going to move through the DFA. And you will always start at the start state, and you'll follow along these paths in accordance with those directions. For example, if I were to read you if I were to provide you a DFA and I were to read you a string, maybe 10110, what you would do is you would start here and then you would follow the transition of 1, follow the transition of 0, 1, 1, 0. And if you end up in a final state at the end of my reading that string, that string that I've read is one that's permissible. If you end up in a state which is not a final state after my reading of the string, that indicates that the string that I've read is not permissible. So all three of these capture the idea of talking about what strings are allowed, what strings are not. I want to formalize for you what a DFA. I want to give you a little bit of explanation for the formalism behind a DFA. And for this, I'm going to give this example. Let's say we have a start state Q0, or I'll call it Q1, Q2, Q3, 0, 1, 0, 1, 0, 1. When we talk about a DFA, there are a few components which we are going to see. There are a few components which make up the description of this DFA. And we have Q, that's the set of states, Q1, Q2, Q3. We have delta. This is a transition function, so this is a set of states. This is a transition function going from Q cross A, going to Q. What this is saying is my input to this function tells me what state I'm in and what character I'm hearing. And this output tells you which state do I go to. For example, in this DFA, delta of Q0, 0, not Q0, Q1, 0 is Q2. Well, this is saying if I'm in Q1, I read a 0, we go to Q2. There's a Q0. This indicates for you the start state. In this case, Q0 is equal to Q1. We have F, which is the set of final states. And in this case, the set of final states is just the state Q3. I hope that it's clear that when we draw that by stating this formalism, we can, once I state perhaps, even if I state this formalism, it will be permissible. You will be able to draw out the picture representing it. I tell you what all the states are. You can draw the circles for the states. I tell you the transition function. If I'm in this state and this character is red, I go to this state. So that gives you all the arrows. This one tells you where to start. This one tells you where to end. Going to use what is question 6 on the practice questions as a running example for the various ways that we manipulate DFAs. So let's say we have a language R, and R consists of strings, consists of all binary strings. So just so that we're not confused, maybe I can make this, I'll make this L. L here, this is a language. It consists of all binary strings with 111 as a substring. And first, let's say like we want to draw out a DFA for this. This here is an English description of the language, and somehow we want to draw out a DFA that will capture exactly this set of strings. It's important that when you draw the DFA, that you don't capture too many strings, so that you don't capture like strings that are outside of this language, nor do you capture too few, which is you capture strings, like some strings inside this language don't get accepted by your DFA. Your DFA must capture exactly the strings corresponding to this language. One of the ways that we could do this is not necessarily a hard and fast rule, but this is a heuristic. This is a perhaps a good way of thinking about it, so that it will help you to draw a DFA given perhaps maybe an English description, is to think about the states as having meaning. Up here, when we have formalized the DFA, we sort of like extrapolated out all meaning from the states. We labeled them like very like undescriptive names, Q1, Q2, and Q3. But when you're given an English description like this, to draw a DFA for it, it will help if you give the states some meaning. And so let's say we're here. I'm going to start with my start state here. And I want my DFA to accept all binary strings that contain somewhere inside of it a 111. Now, what's one of the strings that has to be accepted? It has to accept 111, right? And so if we're going to draw a DFA which accepts all binary strings, we at least want to get something that accepts 111. So one perhaps trick that you can go with is that when you're trying to get an English description, start with some really, really obvious example and make sure that works. I'll do something like this: 1, 1, 1, and this should be fine. Now, the intuition behind why I did it like this is that each of these states, imagine if you're checking a string whether it has a 111 inside, and while you're checking it, how do you actually check whether there's a 111? If you see a 1, you have to like sort of make a mental note to yourself, okay, I have 1, 1. Following that, if you see another 1, then you have to make a second mental note saying, all right, now I've got 2 1s. And then you look at the third one, and if you get a 1, then you're saying, okay, I've gotten the 3 1s. So effectively, what these states represent is, here I have nothing. Here I have nothing. The second state, I have a 1. This state, I have a 1, 1. This state, I have 1, 1, 1. And a DFA, one thing to also remember about DFAs, in DFAs, every state needs to be fully specified in terms of the transitions. In this case, my alphabet, the set of characters I'm talking about is 0 and 1. So that means that every state has to have a transition for 0. Every state has to have a transition for 1. In the case of a DFA, you want to make sure that your transitions are fully specified, that you don't like leave one out or something like that. Let's say I'm here. I've got the transition for 1. What do I do for the transition 0? Well, if I'm here, I have nothing. I read a 0, I still have nothing. If I'm here, I have the transition for 1. But if I read a 0, I go back to having nothing because I have to like restart the count of 1s. If I'm here, I have 2 1s, and I read a 0 back here, because once you read a 0, you're back to recounting the 1s. Once you reach here, well, it doesn't really matter what I keep reading. It doesn't matter if I read 0s, 1s, whatever. This state indicates I've already gotten my 1, 1, 1. Now let's say we're provided with this and we want to generate for ourselves a regular expression which describes this DFA. And the technique to do this is that we want to look for things of this form. We want to look for something that looks like this. No. We want to look for something that looks like this. Let me call this U, V, Y. I want to look for some kind of structure that looks like this and draw instead a transition here with the regular expression U, V star, Y. I have to read U, I have to then read V 0 more times, and then I have to read Y. I want to look for some kind of structure that looks like that. And the idea is that slowly, if I can notice how I've thus converted this kind of thing into a transition like this, and therefore I can by progressively doing this, I can remove kind of this state here. And progressively, as you remove these states, you want to get it down to something that maybe looks something like this. So you want to kind of remove states until you can get it down to something maybe that looks like this. So let's say we have our DFA here. Now what's tricky is that this loop is looking really important, but it's possible this loop doesn't exist. In the case this loop doesn't exist, you just have U, Y. And so what we do in order to formulate the regular expression is we want to do some kind of deletion of these kind of states. And which are the states we want to delete? We want to delete everything except for the start and the final state. We want to delete everything except for the start and the final state. So we want to somehow catch all of those middle ones out. I somehow want to get these 2 middle ones out. Let's try to get this one out first. Now, in order to remove one of these, you sort of need to take into consideration all of the transitions which are popping out of this middle state. Otherwise, if I don't take into consideration all the transitions that are coming out of this, then when you delete it, you will somehow have lost some directions for where to go. In other words, you want to be able to capture all the transition information in here before you take it out. So somehow I want to delete this, and somehow I want to take away all the transition information that's coming out of this before I delete it. And what's that transition information? It's the 0 and it's the 1. So for the 0 case, if I want a 0 case doing something like this, the path that I'm looking for is starting here, 1, no loops, 0. What does that correspond to? Instead of doing 1, 0, I'll just say, well, I can either do 0, or if I read a 1, 0, I end up back here. Right here, we're generating an NFA, more or less. I'm generating an NFA. Now, how about the 1 coming out? Well, I can also get a path here that goes like this. That's a 1, 1 to get here. So I can effectively do this one, and I can draw a line, draw a transition here, which is what happens when I do a 1, 1. So I still have everything else left. erase this part for now. Now, again, I wanted to delete this one now. I only want to end up with my start and final state. I don't want to have anything. I don't want to have any of these intermediate nodes. What's the transition information coming out of this intermediate one here? It's a 0. It's a 1. So I'm going to look for that path. If you remember that picture, the path with that thing in the middle, I have a 1, 1, 0. A 1, 1, 0 gets me back here. So here I have a 0, 1, 0, 1, 1, 0. And if I have a 1, I come here. So a 1, 1, 1 gets me here. So how do I make this into a regular expression? Well, if I start here, I either have a 0, union 1, 0, union 1, 1, 0. That I repeat 0 more times, followed by a 1, 1, 1, followed by 0 or 1, repeated. I want to now also give, so this is how we convert an automaton into a regular expression. Now I want to give an example. Let's say we have a language T, and this language T is 0, union 1, 1, star. Now I'm going to construct an NFA for this language. And remember, you have this power of this lambda transitions, which is like effectively teleportation. Effectively teleportation. Because how am I going to create this? Well, here, I'm going to start from the start state. Either I read a 0, or I read a 1 and then a 1. So here I'm going to create an NFA. And which are the final states? Well, I guess I can read nothing. If I read the 0, I want to make sure that's a final state. If I read the 1, 1, I want to make sure that's a final state. And I want to be able to like repeat this a bunch of times. So in effect, we have these lambda transitions, which is saying, well, if I got the 0, I want to like teleport back here so that maybe I could get the 1, 1 again, and then I'll teleport back here, and then maybe I'll get a 0, and then I'll teleport back, and then 0, 1, 1, and so on. Now, the important thing is that the lambdas don't actually add any more expressive power to an NFA than a normal NFA without any lambdas. And so one of the procedures that you might want to know how to do is to convert something with lambdas, to convert this NFA with lambdas into something without lambdas. And the way to do this is you want to remove essentially all the lambda transitions. You want to effectively remove all the lambda transitions. So step 1, any state that can, I'm going to call this lambda teleport to a final state is final. In other words, even if I had some like non-final state here, but then can lambda teleport to a final state, even if I had something maybe here, this can lambda teleport to a final state. Those become final. And then you look for paths of this form, lambda lambda, so on, A. And then you connect this state here to this state via an A. And so essentially what you do is you take away all the lambdas, you take away all the lambdas from this thing, and then you put in the right transitions based on these lambda paths. So here we have these two lambda transitions. I want to get rid of them. I'm going to draw out my states again. Step one, well, all the states that can lambda into a final state are already final, so we don't have to change anything there. I've got here 0, 1, 1. Now I've removed all the lambdas. So what other things do I essentially need to look for these paths and fill them all in. Here. Can I lambda, can I do something like this to a different state? The answer is yes, I can do a lambda, then a 0. It's important that you look for a bunch of lambdas and then one single non-lambda. This is a non-lambda. So you want to look for these paths of a bunch of lambdas and then one single non-lambda. Look at this state here. Anything for a bunch of lambdas and then one single non-lambda. Lambda 0. That means that I can just draw a 0 transition back to here. How about lambda then 1? That means I can draw one transition from here to here. How about this state? Well, there are no lambdas coming out of it, so I don't have to do anything. Nor this one. But here I can do a lambda 1. That means I get a 1 going from here to here. And here I can do a lambda 0. That means I get a 0 path from here to here. And this gives you your NFA with no lambda transitions. Now, just because, so here we have given an example to show you that I can go from an NFA with lambdas to an NFA with no lambdas. And so therefore, the expressive power of the NFA lambda, just because you have these lambdas, doesn't really add any more ability. It just makes it maybe easier to draw for something. But in effect, what you can do with the NFA lambda, you can also do with an NFA. Now, I'm going to show you that this NFA is also has the same expressive power as that of a DFA. Yeah. Sure. Okay. So what I do is I draw this setup, this skeleton out, and you take away the lambda transitions. So in effect, I keep this skeleton here, but I have made all the lambda transitions disappear. I in fact keep this, and then you basically look for all possible paths where you have a bunch of lambdas to begin with and then a non-lambda. And you look in your original one and you look for every possible path where you can have a bunch of lambdas and then one non-lambda. And then that makes, and then so then you, if you find one of those paths, then you add this transition in to your skeleton, which is you go from here to here and just transition with this non-lambda character. I start from this state here. I look for, are there any paths that start with some lambdas and get to one non-lambda? There's one of them is this, then this. This starts with some lambdas and then has one non-lambda. So in effect, when I do this, I've only read a 0. And so by reading a 0, I can go from here back to itself. This path of lambdas, then one non-lambda, starts from here, ends here, and the special character in that special non-lambda character is 0. Therefore, I draw a transition as so. I look again here. Are there any more? Well, there's lambda 1. And so this lambda one non-lambda path starts from here, ends up here with the special non-lambda character of 1. Therefore, I draw a transition like this, 1. Is this good? Yeah. It's just and I mean anything that will generate a valid DFA works. It's just this is a procedure that maybe has some generality in which now I need to draw this NFA back. 0. That's a 0. So the one last thing about automata is that now I want to show that this NFA is able to give you the same expressive power as that of a DFA. And so let's say that we have this NFA here. I don't know if it's full. It may already be almost fully specified. Just this one doesn't have a 0. But let me just draw maybe a different example because this one is pretty close to a DFA already. I'll draw here a simple NFA, which is 0 and then 1. I have 2 states, Q0 and Q1. If I want to go from an NFA to a DFA, what I'm going to do is I'm taking my NFA, my new states are subsets of the set of states I have here. In other words, I have null set of Q0, set Q1, set Q0, Q1. These are my states. How do I label the final state? Which ones are final? The ones that are final are the ones that so notice that each state is now labeled with a set. If this set contains, if even one of the states inside the set is a final state, I label it as final. So here, this one Q0 is not final. This one contains Q1 is final. So I make this final. Here, this contains Q0 and Q1, but Q1 is final. So I have at least one state which is already final. So I make this one final too. Now, how do I draw the transitions? I need to remember a DFA needs to be fully specified. So I need to have a Q0, and when I read a 0, it has to go to, I have to give a transition for 0, I have to give a transition for 1. If I'm in nothing, I read a 0 or a 1, I'll end up back in nothing. Q0, if I read a 0, where can I end up? Well, I can end up in Q1 only. If I read a 1, where can I end up? I can end up nowhere. Comes here. For Q1, if I read a 0, where can I end up? Nowhere. If I read a 1, I can only end in Q1. If I'm in Q0 or Q1, I read a 0. What are the possibilities? If I'm in Q0 or Q1 and I read a 0, the only possibility is I get to Q1. Here I go nowhere. If I'm in Q0 or Q1 and I read a 1, what's the only place I can go? Just here. And that gives you the DFA. One last topic, which is the idea of the pumping lemma.
Sometimes like you won't use your like the most number can have pretty long. If it's a but it will be
Yeah. Oh, is it not? Okay, then I won't cover it. Sorry. All right. So since the plumbing lemma is not in the final, I'm not going to cover it here. Why don't we break for about 5 minutes, and when we come back, I'll talk about combinatorics and probability. Yeah.